Holding in progress.
So this is homework 5, part A. For the first part of this video, we're going to be using heat and mass transfer analogy to derive and explain the Lewis relation, right? And so we can do that using a couple of different equations here, right? So we have our Sherwood number, right, which is our convective mass transfer over our diffusive mass transfer, right? And then to the right of that, we have the Nusselt number, right? Which is our convective heat transfer over our conductive heat transfer, right? And we can use these two equations with the Reynolds number to then get the Sherwood number or the Schmidt number and the Prandtl number, right? So we know that the Sherwood number is equal to the Reynolds number to the 1/2 times some constant, right? Multiplied um, by the Schmidt number to the 1/3, right? So that's how these relate. So we're able to use the Sherwood number with the Reynolds number to get to the Schmidt number. And the same thing is true of the Nusselt and the Prandtl, right? Nusselt equals some constant Reynolds number to the 1/2 times the Prandtl number to the 1/3, right? And that's how we're able to relate those two, right? And so when we do this, we know that the Sherwood number over the Nusselt number equals the Schmidt number over the Prandtl number all to the 1/3, right? And that equals our Lewis number to the 1/3, right? And so now that we have that, we can plug in these numbers, right? Or we can plug in these values, right? So Kc delta over our DAB over our K. Sorry, this is wrong, right? So what we want to do is we're just gonna multiply, right? So it'll be K um, over DAB times, right, K over H delta, which then will get you KC K over DAB, right? These cancel times H. And then we can do the same thing for the other side and get mu over rho DAB times CP, or no, times K over CP mu. The mu's cancel, right? That's our momentum transfer, right? And so we end up with K over rho CP DAB, right? And this would be to the 1/3, right? And so these then equal the Lewis number to the 1/3, right? And when we look at water, we know that the Lewis number is 1, right? So if we set this equal to 1, we then know that Kc times K over DAB H equals our K over rho CP DAB equals 1, right? So with that, we can then simplify this expression down and solve for H, right? Which is the analogy that we're going for, right? And when we do that, right, our DABs cancel, our Ks will cancel, and then we will be left with H equals rho CP, right, multiplied by our KC, right? And this is the analogy that we're trying to derive, right? This is our Lewis relation that we were able to get using our heat and mass transfer analogies, right? So we found that H, right, equals our rho CPKC, which is um, the Lewis relation that we were looking to derive, right? Next, we're going to talk about a couple of different situations. The first is going to be um, evaporative cooling, right? We're going to use our heat and our mass transfer here, right? So we have a surface with a bubble of, we'll say, water, right? This is liquid at some temperature water, and we have air flowing above it, which will be at T air, right? And so for um, right, what we have here, right, we have our Q going into the water, right? So that's our heat transfer, but then we also have the water going into the air, right? So that is our mass transfer, right? And so if we write these equations out, right, um, our heat equation, right, that is going to be our H times our area multiplied by the change in our heat, right? So it's going to be T air because the heat is coming from the air, minus our T water, right? And if we look at this, this whole expression will have the units of joules per second, right? And so for our mass, right, we have our Kc times our cross-sectional area, and then the different, or the gradient here is going to be our concentration, right? So we have the concentration of the air minus the concentration of the water, right? And so this has units of moles per second, right? And so actually this is the concentration of the water minus the concentration of the air. But right, so this has moles per second, and we want to be able to relate these two equations, right? We want to set them equal to each other. And so we have to get this bottom to be in joules per second. So what we're going to use is going to be our enthalpy of vaporization, right? Which has units of joules per mole, right? So if we multiply that, we'll end up with joules per second. So we can just add our um, our enthalpy of vaporization to get to joules per second. And so now we can set these two equations equal to each other. HA T air minus T water equals lambda KCA CW minus CA, right? Now, like what we just solved for in the last thing, we know that H equal to rho CP KC. So we plug that in. I'm going to move this up. Right, we can plug that in for H. So it'll be rho CP KCA times T air minus T water equals lambda KCA, concentration of water minus concentration of air, right? And if we look at these two equations, our KCA cancels out, which then results in rho Cp, change of temperature of the air and the water, equals lambda times Cw minus Ca, right? So this is our final equation for evaporative cooling that we were able to use the Lewis relation that we found in the last part to get this equation. Next, what we'll look at is, let me just draw a line here. Next, what we'll look at is adiabatic saturation temperature. And this last part, right? We're at steady state here. That's an assumption that we made so that this all works out. But when we're looking at adiabatic saturation temperature, right, we have a tube here, and we'll say that water is lining the walls, right, but it's not filling the tube, right? So, sorry. Right, we'll have air flowing through the middle, right, and this will be at T air 1. And then we have the water at temperature 1, right? So T water 1, right? And one thing going on here, right? So we have our air temperature coming out, T air 2, and then we have our T water 2. These two are going to be the same, right? The temperature of the air and the temperature of the water are going to be the same. So we know that right, our saturation is going to be 100%, right? So our relative humidity is 100%, right? So if we do the same thing that we did for the last thing with our evaporative cooling, right? We look at the heat and mass transfer, right? So our heat, once again, we have our HA, and then what we will have for temperature is our T air 1, right? And then it would be T air 2, but that equals our T water 2, right? So we can say TW2, right? And that's still in joules per second. And then for mass, right, we have our KCA times the concentration of the water minus the concentration of the air. And then once again, times our lambda to get to joules per second. And this is actually not water. This is air 1 and then air 2. Sorry. Right. And so we can set these equal to each other once again, right? Our HA, T air 1 minus T water equals K lambda KCA, concentration 1 minus concentration 2. Right. We can then plug in what we found for H, right? That's our rho CPKC. And once again, we can cancel out our KCA to get rho CP TA 1 minus TW equals lambda CA1 minus CA2. Right, and so we can now compare these two equations that we found. So if we look at these here, where is this one? Here we go. Right, so if I take these two equations and we're looking at them, right, right, we see that they're very similar. And so if we're looking at the dry bulb temperature, right, what we want to solve for is the concentration of well, actually, before we do that, right, we know that we're going to be looking at the concentration of our air, right? So we have our air 2 minus our air 1, right? So if we isolate that, we can get Ca2 minus Ca1 equals rho Cp Ta1 minus T water over lambda, right? And so for our dry bulb temperature, right, we know that in this scenario, we have no saturation at 0.1, right, over here. So we're going to be solving for Ca1, right? So Ca1 equals Ca2 minus rho Cp Ta1 minus Tw over lambda, right? So that's how we were able to find our dry bulb temperature, because we know that the saturation at temperature 1 um, doesn't have any water in it, right? And so when you're looking at like the sling spectrometer, right, the dry bulb is just swirling around in the air, and then the wet bulb, right, that's when you have the wet paper towel wrapped around the end of the thermometer, and so that's why it's wet. And for that case, right, we want to look at the concentration too, because our relative humidity is 100%. So our concentration of water in the air will be 100%. Right. So we know that Ca2 equals Ca1 plus rho Cp Ta1 minus T water over lambda. Right. And so we were able to relate adiabatic saturation temperature with the with the evaporative cooling to then get our dry and wet bulb temperature equations. Um, so yeah, that is homework 5 part A.